Imagine an $80,000 electric delivery van just goes completely dead on Interstate 5.
Right, just absolute zero battery.
Yeah, exactly. The battery hits zero. And, the driver does what anyone would do in that situation. They call a traditional roadside dispatch.
Which makes sense. I mean, that's the standard operating procedure we've all been taught for decades.
Right. And a standard tow truck arrives to rescue the vehicle.
Or at least they think it's a rescue.
Exactly. Because by the time that tow truck drags the van to the nearest commercial dealership, that so-called rescue has literally melted the vehicle's drivetrain from the inside out.
It's honestly devastating.
It really is. We are
Yeah.
talking about like maybe $20,000 in catastrophic damage.
And all because the old standard operating procedure for a dead battery, the internal combustion rules,
Yep.
is actively, secretly destroying modern commercial EV fleets.
It really is the ultimate logistical paradox.
Yeah, the very mechanism designed to save the asset is the exact mechanism that totals the asset.
Okay, let's unpack this, because welcome to the deep dive. Today, we are bringing you right to the front lines of commercial mobility and fleet management.
It's a really critical space right now.
It is. We are tearing into this fascinating stack of operational guides, service profiles, and regional logistics data.
Specifically stuff emerging from the Pacific Northwest, right?
Yes, specifically focusing on the methodologies of Portland Mobile EV Rescue. And our mission today is highly specific.
Right, because if you are managing a fleet or driving rideshare or just looking at the bottom line of commercial logistics,
This is critical for you to hear. We are exploring how you take what seems like an unavoidable, crisis-like electric vehicle range loss and engineer it into a managed, predictable, operational metric.
I mean, we really have to establish right off the bat that this is not about consumer range anxiety.
Oh, absolutely not. We aren't talking about like a family having to kill 30 minutes at a highway diner waiting for a plug on a road trip.
No, not at all. We are talking about the hard, unforgiving mathematics of commercial uptime.
Time is literally money here.
Exactly. In the logistics sector, variables are everything. I mean, a well-designed supply chain or a high-functioning fleet network survives entirely on the concept of what we call the strategic buffer.
A strategic buffer. Okay, break that down for us.
Sure. So you buffer your inventory in warehouses to absorb supply chain shocks, right?
Right.
And you buffer your delivery windows to absorb unexpected traffic congestion. You buffer your staffing to handle, like, seasonal volume spikes.
So it's all about building in a cushion for when things inevitably go wrong.
Precisely. But historically, when we look at the legacy era of diesel and unleaded fleets, nobody really had to buffer for the actual energy source.
Because the fuel was just everywhere.
Yeah, the buffer was just the built-in reality that there was a gas station on every single corner and refueling took 5 minutes.
Right. The grid for internal combustion was omnipresent. It was immediate.
But as commercial fleets transition to electric architectures, the industry is slamming into this brutal realization
Which is what?
that you can no longer rely on omnipresent geography for your energy buffer.
Wow. Yeah, that makes sense.
Battery depletion cannot be treated as a sudden catastrophic anomaly that you just deal with on the fly anymore.
It has to be treated as a calculated operational reality.
Exactly. You have to build a strategic buffer for power itself internally within your own operational model.
Think about your own service level agreements right now. Like if you are listening and operating a fleet of electric Sprinter vans in Portland.
Maybe you're a commercial bakery delivering highly time-sensitive goods to cafes.
Right, or a medical courier moving lab samples across the metro area. What is your current protocol if a van goes down on a Tuesday morning?
That is the million-dollar question.
Because the sources we are looking at paint a terrifying picture of the immediate financial bleed when a commercial EV becomes immobilized.
When that battery hits zero, the bleeding starts instantly. And it compounds way faster than most dispatchers even realize.
So let's talk about the initial phase of that bleed.
Well, the very first thing is the immediate halt to revenue generation.
Because an immobilized van means the driver's just sitting on the side of the road.
Yeah, they're on the clock, accumulating hourly wages, but producing zero output.
But it's not just the driver. The cargo inside that van is also immobilized.
Exactly. And in commercial logistics, missing a rigid delivery window doesn't just mean a delayed package.
No, it triggers a cascade of financial penalties.
You're looking at damaged client relationships and potentially even lost contracts.
But I want to push back on the root cause for a second.
Okay, sure.
Because anyone looking at a modern fleet dashboard might be thinking, wait, isn't range depletion just a massive sign of poor route planning?
I hear that argument all the time.
Right, because we have sophisticated telemetry now. The dispatch dashboard tells you the state of charge.
And the driver has a massive screen right in front of them telling them their range.
Exactly. So why are these vehicles even getting close to zero in the first place? Shouldn't we just point the finger at driver error or maybe poorly optimized routing software?
I mean, blaming the driver or the routing algorithm is sort of the traditional reactive way of looking at fleet management.
But it's not accurate.
It assumes that a commercial vehicle operates in a vacuum.
Ah, right.
But the operating environment in a place like the Pacific Northwest is highly dynamic. And honestly, it's inherently hostile to static battery predictions.
Because the algorithms can only guess so much.
Right. A routing algorithm might calculate a delivery path based on optimal ambient temperatures and totally clear traffic.
But then, a massive storm system rolls in off the coast.
Exactly. The temperature drops by 15 degrees out of nowhere.
And cold is the enemy of batteries.
Yes. Suddenly, the vehicle's battery management system has to divert a huge percentage of its kilowatt hours away from the drivetrain.
And push it into the thermal management system.
Precisely, just to keep the battery cells within a safe operating temperature so they don't get damaged.
Meanwhile, the driver hits an hour-long gridlock on Interstate 5 because of an accident.
Right, so now the wipers are on, the cabin heater is blasting, the battery is conditioning itself.
All while the vehicle is barely even moving?
Yes. So that 20% safety margin the algorithm calculated at the start of the shift, it literally evaporates before the driver even reaches their third stop.
Oh, wow. So the unpredictability of the environment just completely overrides the predictability of the software.
That's exactly what happens.
And when that margin evaporates, the fleet manager is thrown headfirst into what the Portland mobile EV rescue materials call the price trap.
The price trap is brutal.
It really is. And this is where the financial model of traditional roadside rescue completely breaks down for commercial EVs.
We should walk through the actual sequence of events here.
Yeah, let's go step by excruciating step of what happens when you call a standard tow truck for a stranded electric delivery van.
So the price trap is essentially a compounding economic penalty that punishes the fleet operator at every single stage of the recovery process.
What's stage one?
Stage one is just the physical hookup. You are paying a premium emergency rate for a heavy-duty flatbed to just arrive at the location.
Which is already expensive.
Very. But the critical failure of the traditional model is the destination.
Right.
A tow truck cannot simply drag a commercial EV to a public fast charger.
Wait, why not? I mean, physically, they could just drop it off in a parking lot.
Physically, perhaps, but practically and legally, it's a total non-starter.
Because of liability.
Partly liability. Traditional tow operators cannot guarantee that the public charger they drop you at is actually functional.
Oh, that makes sense. You don't want to get towed to a broken charger.
Exactly.
Yeah.
And furthermore, they cannot drop a dead, unmovable commercial vehicle in a way that blocks a public charging stall or a retail parking lot if the station happens to be offline.
Right. A dead Sprinter van is basically a giant roadblock.
Exactly. The liability and the logistics of trying to motor a dead 6,000-pound van perfectly into a tight charging bay, it's a nightmare scenario for a tow operator.
So where do they take it?
They default to the only guaranteed secure location.
The dealership.
Yeah. They tow the asset directly to the manufacturer's commercial service center or dealership.
And this is where the jaws of the trap really snap shut, right?
Oh, absolutely.
Because you've just paid hundreds of dollars for the emergency tow. But when that van arrives at the dealership, it does not get greeted by a technician holding a fast-charging cable.
Not even close. Dealership service centers operate on strict queuing systems.
Right, based on scheduled maintenance and high-priority warranty repairs.
So a dead van dragged in off the street, it goes straight to the back of the line.
It enters a diagnostic purgatory.
That's a great way to put it. The service center cannot just plug it in and hand you the keys an hour later.
Their protocols don't allow that.
No, their protocols require them to fully intake the vehicle, assign a specific technician, and run a full diagnostic suite.
Just to make sure the battery depletion didn't trigger any secondary failures?
Right, like low voltage failures.
Yeah.
And they have to safely cycle the high voltage system back online.
And in a busy commercial dealership, that process might take 3 to 4 days.
Easily.
So if you are a fleet manager listening to this, calculate the math on this for a second. You haven't just lost the $200 tow fee and the diagnostic fee.
I know those are just a drop in the bucket.
Right. If your delivery van generates, say, $800 a day in route value, and it sits in a dealership lot from a Friday afternoon breakdown until a Tuesday morning diagnostic check.
You have hemorrhaged thousands of dollars in pure gross revenue.
Plus the hidden costs of rerouting.
Oh, the rerouting is a nightmare.
Because to cover the downed route, you have to cannibalize the schedules of your remaining operational vehicles.
You stress your other drivers, you push your remaining assets harder, and you inject chaos into a system that relies on complete precision.
So the cost of traditional towing isn't just the invoice from the tow company.
No, the true cost is the multi-day destruction of your commercial uptime.
But the financial bleeding is just one side of the coin.
Right, there's a whole other issue here.
The operational guides from Portland highlight an entirely different threat that fundamentally changes how fleet managers need to view roadside rescue.
We really have to pivot from the economic risk of downtime to the actual physical risk.
Because traditional rescue methods pose a massive threat to the fleet vehicles themselves.
When it comes to high-end commercial EV platforms, and the sources specifically call out vehicles like Teslas, Rivians, and modern electric cargo chassis, the cure can literally destroy the patient.
We are looking at severe, irreversible damage to the structural integrity of the electric vehicle's drivetrain.
Right, and to understand why standard towing is so dangerous, we really have to contrast the mechanical architecture of an EV with a legacy gas vehicle.
Let's break that down because I think a lot of people assume a car is just a car when it's rolling down the highway.
It's a very common misconception.
With an internal combustion engine, you have a transmission.
Right.
When the car dies, the tow truck driver pops the transmission into neutral.
Which physically, mechanically disconnects the engine block from the drive wheels.
The vehicle basically becomes a heavy wagon.
Exactly. The wheels can spin at 60 miles an hour down the highway, while the internal components of the engine remain completely stationary.
The mechanical decoupling is absolute.
But an electric vehicle operates on a completely different paradigm.
How so?
In most modern EV architectures, particularly the direct drive permanent magnet motors used in these high-efficiency commercial fleets, the electric motors are directly, permanently connected to the wheels.
Via a reduction gear.
Yes, via a reduction gear. There is no traditional transmission.
Wait, so there's no physical neutral gear?
There's no true physical neutral gear that disconnects the rotor inside the motor from the axle.
Oh, wow. So the wheels are always connected to the motor.
Always. And this ties directly into how these vehicles achieve their range in the first place.
Because they rely on aggressive regenerative braking.
Regenerative braking is the core of the issue here. In normal operation, when a driver lifts their foot off the accelerator, the forward momentum of the vehicle keeps the wheels turning.
And because the wheels are physically linked to the motors, the turning wheels force the internal rotors of the motors to spin.
Exactly.
Yeah.
Which effectively turns the electric motors into generators.
That's fascinating.
They create a massive amount of electrical current. Specifically, it's called back electromotive force, or back EMF.
And usually that back EMF is a good thing, right?
Oh, it's fantastic.
The vehicle's battery management system, the BMS, takes that generated electricity, routes it through the inverter, and dumps it safely back into the high-voltage battery pack.
Which extends the vehicle's range. It is brilliant engineering.
It's brilliant when the vehicle is awake and actively managing the flow of energy.
Right. But it is precisely what makes traditional towing catastrophic when the vehicle is dead.
Because if an EV has suffered total battery depletion, its internal computers, its battery management system, and its thermal cooling pumps are completely shut down.
But the brain of the vehicle is totally offline. It cannot protect itself or route that power.
So imagine this scenario for a second. A standard tow truck arrives.
Maybe they don't have a full flatbed.
Right, or maybe the van is parked in a weird way, so they have to hook it from the front.
Right, they lift the front wheels off the ground, leaving the rear drive wheels right on the pavement.
And they start dragging this dead EV down the highway at 50 miles an hour.
Because there is no physical disconnect, those rear wheels are spinning furiously against the pavement.
And because they are directly geared to the electric motors.
They're forcing the rotors inside the motor casing to spin at thousands of RPMs.
So the motors are acting as massive generators, producing this huge tidal wave of raw electrical current.
But remember, the vehicle is dead.
The battery management system is offline.
Right. The contactors to the main high-voltage pack are open, meaning the battery cannot physically accept the charge.
So that raw, unmanaged electricity has absolutely nowhere to go.
It's like forcibly manually spinning the blades of a high-powered wind turbine that has been completely disconnected from the electrical grid.
Wow, that is a great analogy.
The physical energy is being converted into electrical energy, and if it can't flow into a battery, the resistance creates friction,
And that friction instantly converts into intense, concentrated heat.
massive heat. The pressure completely floods the vehicle's inverter. The components overwhelm.
Because the liquid cooling pumps that would normally manage that thermal load are offline.
Exactly, because the 12-volt system and the high-voltage system are both dead.
So what happens to the hardware?
The heat literally melts the high-voltage wiring. It cooks the silicon carbide chips in the inverter.
Oh, man.
It literally melts the intricate stator coils and the highly sensitive electromagnets inside the drive unit itself.
You're cooking a multi-thousand-dollar piece of highly engineered hardware from the inside out simply by dragging it down the road.
And the irony is just staggering when you think about it.
Because you are paying a tow-truck driver premium emergency rates to save your stranded asset.
And in the process, they're actively destroying the single most expensive component of the vehicle.
The resulting damage is not something you can just patch either.
Oh no. The sources explicitly note that this leads to multi-thousand-dollar repair bills, very often requiring the complete replacement of the entire drive unit.
And this introduces the secondary and perhaps even more devastating financial blow.
The warranty void.
Right, because modern commercial EVs are essentially rolling data centers. They log absolutely everything.
Every single rotation, every temperature spike, every voltage anomaly is recorded by the vehicle's CAN bus system and telemetry data loggers.
So when that destroyed vehicle finally gets pushed into the dealership service bay,
The very first thing the manufacturer's technician will do is plug in and pull the logs.
they will immediately see that the wheels were rotating at high speeds while the vehicle systems were offline.
They will see the massive thermal spikes in the inverter.
They know exactly what happened.
They know it was improperly towed. There is no hiding it.
And they will instantly void the warranty on that drivetrain.
Fleet managers are the stewards of highly expensive capital assets. A commercial electric delivery chassis or a high-end rideshare platform is an investment of $60, $70, maybe $80,000.
So relying on a traditional tow truck is just an unacceptable risk mitigation failure,
Completely unacceptable.
which perfectly frames why the methodology of the rescue is just as critical as the rescue itself.
Absolutely.
The operational guides point out that this is where mobile charging fundamentally changes the paradigm.
By bringing a specialized, self-contained mobile charging unit directly to the vehicle, you bypass the mechanical risk entirely.
The vehicle never has to move. The wheels stay on the ground.
The tires never leave the tarmac. You aren't dragging a dormant generator down the highway.
The mobile service just plugs directly into the vehicle's standard CCS or NACS port.
It delivers a controlled, managed flow of kilowatt hours to safely wake up the battery management system.
It boots the computers and provides sufficient range to drive the vehicle normally to a depot or a fast charger.
And the drivetrain remains completely uncompromised. It really is the ultimate asset protection strategy.
But, analyzing this raises an inevitable question regarding operational behavior.
Okay, what's that?
If the financial penalty of a tow is so compounding and the physical risk to the drivetrain is so catastrophic, why do commercial fleet drivers and logistics operators ever push their batteries that close to zero?
Right. Why take the risk?
Exactly. Why risk getting stranded at all? That is the million-dollar question. If the stakes are this high, shouldn't every fleet driver just pull over and plug in when they hit 20%?
You would think so. But this brings us to the core of the infrastructural reality that these guides from Portland Mobile EV Rescue expose.
The environment they're operating in.
Yes. The answer lies in the harsh geographical reality of the current charging infrastructure in the Pacific Northwest.
Fleet managers are forced to need a mobile backup plan because the primary public grid is deeply structurally flawed for commercial use.
The public infrastructure was designed for consumer convenience, not commercial reliability.
And that's a massive distinction.
Huge. The operational guides refer to the PNW charging infrastructure as a work in progress.
And in the context of commercial logistics, work in progress translates to operational friction.
They specifically cite broken plugs in Vancouver, massive time-killing queues at stations in Portland, and the constant unpredictable plague of icing.
Icing. We all know the headache of icing internal combustion engine vehicles blocking EV spots.
It's annoying for anyone.
But when you look at it through the lens of a fleet manager, it is incredibly infuriating.
Imagine a commercial cargo pilot bringing their plane in for a scheduled refueling stop, only to find someone parked a lawnmower on the runway and just walked away.
That's perfect. It completely severs the logistical chain.
It does. But the sources highlight specific danger zones that really illustrate the failure of the public grid.
They point directly at the Portland International Airport PDX.
Yes, describing the parking lots there as a complete charging desert when you are in a hurry.
The airport ecosystem is a fascinating microcosm of this infrastructure failure.
Because you have an incredibly high concentration of commercial EVs.
Specifically, rideshare drivers for Uber and Lyft constantly cycling through to pick up arriving passengers.
And these drivers operate on razor-thin time margins. The app's algorithm rewards drivers who are actually in the queue and available.
So, if you are a driver sitting in the PDX cell phone waiting lot and your battery drops to 10%, you face an impossible choice.
Do you abandon your spot in the queue, forfeit the lucrative airport surge pricing, and drive miles away to hunt for a public fast charger?
Or do you gamble? Do you pick up the passenger and just pray their destination is near another charger?
And most drivers, dictated by the economic pressure of the gig economy, will gamble.
They stretch the range.
And this leads to the next danger zone highlighted in the guides, Interstate 5.
The sources point out that running out of power on I-5 is not just an inconvenience.
No, it is a severe, life-threatening safety hazard.
The shoulders on I-5 are notoriously narrow in certain stretches.
Traffic moving at 70+ miles an hour.
In the rain, often with massive commercial freight trucks flying past.
This introduces the 247 urgency angle, heavily emphasized in the Portland operational materials.
They paint a very specific, visceral picture of infrastructural failure.
Picture this. It is 2 a.m. in Portland. It is raining.
The temperature has dropped, sapping the last bit of range from the battery.
And the vehicle finally hits 0%.
You are stranded in the dark, on a narrow shoulder, getting buffeted by the wake of passing semi-trucks.
Every single minute you wait for a traditional tow truck is a minute that your driver, your employee, or you as an independent operator are physically unsafe.
But let's assume the driver actually managed to limp the vehicle off the highway.
Okay, so they pull into a retail parking lot at 2 a.m. where the dashboard map indicated a public charging station.
They arrive, only to find the station is in a dark, unlit, completely isolated corner of the lot.
And the screen on the charger is smashed.
Right. Or the physical cable has been vandalized.
Or the credit card payment gateway is offline.
Which brings me to a massive point of friction I had when analyzing how dispatchers route these vehicles.
What's that?
I was looking into how these dashboard apps actually talk to the chargers, because the digital map on the dashboard says, yes, there is a charger at this exit and it is available.
Right.
Why is the technology lying to the drivers?
This is perhaps the most critical disconnect in modern EV logistics. The sources call it the no-charger reality.
The no-charger reality. I like that term.
You really have to understand the data architecture between the EV charging networks and the dashboard APIs.
Because digital maps show digital intent, right?
Exactly. They do not show physical reality.
So what exactly is the API measuring if it's not measuring reality?
Well, the charging networks operate on protocols like OCPP, the Open Charge Point Protocol.
Okay.
When a fleet manager or a driver looks at a digital map and sees a green icon representing an available charging station, that dashboard API is essentially sending a basic heartbeat ping to the charge point operator's server.
A heartbeat ping.
Yes. That server then pings the physical dispenser in the parking lot.
And what does the dispenser say back?
The dispenser replies back, yes, I am receiving voltage from the local grid and my software is online.
So it's just a digital handshake.
Exactly. That API handshake confirms that the station exists geographically and that the internal computer has power.
But that API has zero optical sensors.
None. It has no physical ground truth whatsoever.
So it does not know that a delivery truck backed into the pedestal 3 hours ago and physically crushed the plastic connector plug.
It does not know that a pickup truck is currently parked sideways across 3 charging bays.
It does not know that the locking mechanism on the holster is jammed.
The digital twin of the infrastructure is totally blind to the physical chaos of the real world.
A broken plug on an app looks exactly like a viable, fully functional destination.
But in real life, It is a total dead end.
And for a commercial fleet, an unreliable public charger is a broken link in the supply chain.
If you are managing a logistics empire, you rely on hard, verifiable data and guaranteed outcomes.
You cannot base the success of your commercial operations, the integrity of your SLA contracts, and the physical safety of your drivers on the absolute lottery of public plug availability.
Don't play the lottery with your battery.
That's an exact concept from the Portland operational guides.
And it distills this entire problem perfectly.
It really does. If you are a commercial bakery trying to deliver 50 wedding cakes on a Saturday morning, you do not gamble on whether or not the industrial oven is going to turn on.
No, you ensure you have a dedicated, reliable heat source.
Fleet managers need a dedicated, reliable power source that completely supersedes the unreliability of the public grid.
Which brings us to the operational pivot.
We have established the compounding financial penalty of the dealership price trap.
We have extensively detailed the catastrophic physical threat to the EV drivetrain caused by improper towing.
We have mapped out the infrastructural gap and the API blindness of the Pacific Northwest charging grid.
The stage is basically set for a massive logistical failure.
But this is exactly where the savviest fleet managers are turning this unavoidable friction into a calculated strategy.
If the public grid lies to your dashboard and traditional towing destroys your $80,000 asset, the only logical pivot is to bring the grid directly to the vehicle.
Yes. This is the paradigm shift presented in the materials regarding Portland Mobile EV Rescue and their platform at portlandmobileleafcharging.com.
The concept is radically simple, but logistically profound.
On-demand, mobile power delivery. Anytime, anywhere.
They position themselves as the charger that always works.
And when you fully contextualize the broken public infrastructure and the API blindness we just analyzed, you realize that phrase is not just a marketing slogan.
No, it is an operational imperative.
The guides actually refer to this mobile service as the secret weapon for PNW pro drivers.
Let's look at how this fundamentally alters the day-to-day architecture of a commercial route.
Yeah, take a rideshare driver operating in Vancouver on a busy Friday night.
The surge pricing is peaking. The revenue potential is massive, but the battery is dipping perilously low.
In the old reactive public grid model, that driver has to log off the app. They stop earning money entirely.
They drive miles other way to a public fast charger, just hoping it's online.
They sit in a physical queue behind 3 other cars for 30 minutes.
And then they sit tethered to the plug for another 40 minutes.
They have just sacrificed over an hour of peak earning time, and they burned valuable kilowatt hours just navigating to the charger.
Right. But let's apply the mobile charging strategy to that exact same scenario.
Okay, so the driver knows they need to take a legally mandated meal break soon anyway.
They pull into a safe, convenient parking lot of their choosing.
They call the mobile service.
The power comes to them while they are eating their meal.
The mobile unit plugs in, delivers a high-speed charge directly to the vehicle, and by the time the driver finishes their break, the vehicle is completely replenished.
They instantly log back onto the app.
The downtime is virtually zero because it was overlaid onto planned, necessary downtime.
It maximizes commercial uptime to an incredible degree.
It effectively decouples the commercial asset from the static geographical limitations of the power grid.
So what does this all mean for the logistics professionals actually architecting these massive fleet operations?
I think it represents a complete psychological and operational shift inside the dispatch center.
It changes the entire mindset from reactive panic to proactive management.
Think about the dispatcher. When a driver calls in and says, "I'm at 2% battery on Interstate 5, the dispatcher doesn't have to panic.
They don't have to start calculating the catastrophic cost of a multi-day tow to a dealership lot.
They don't have to worry about the CAN bus telemetry voiding the warranty on a massive capital asset.
Because it becomes a managed protocol.
It's simply about deploying a safety net that is fast, reliable, and immune to the API blindness of the public grid.
It becomes a predictable line item in the operational budget rather than a chaotic, unpredictable disaster.
And this raises what I think is the most critical question for the future of commercial transportation.
What is that?
How do modern electrified fleets define a strategic partner?
In the legacy era of diesel logistics, a strategic partner might have been the company that sold you commercial tires at a bulk discount.
Or a regional maintenance garage that gave you priority scheduling?
But in the electrified era, where energy itself is the unbuffered variable,
A strategic partner is an entity that actively absorbs the friction of the real world.
Absorbing the friction. That is the perfect logistical definition of what a mobile rescue service provides.
By integrating e-rescue and their on-demand mobile charging into their operational protocols, fleet managers are actively stripping away the unpredictability of the environment.
They are making a calculated operational statement.
They're saying, we acknowledge that public infrastructure APIs will fail us. We acknowledge that sudden temperature drops will reduce our algorithmic range.
We acknowledge that traffic gridlock on I-5 will cause unexpected battery depletion.
But instead of falling victim to those variables and getting caught in the dealership price trap, they employ a strategic buffer.
They ensure operations can continue, or at least recover instantly, regardless of smashed public plugs, icing, or 2 a.m. emergencies in the freezing rain.
It is taking